Hey, welcome everybody to DEFCON 1 Science, our third edition. Yeah, I stopped the intro pretty quickly. Guess there were some audio issues there. Wasn't sure if you guys can hear us or you guys were hearing that, so I stopped it. Can you hear us fine? Because if not, then there's no sense of doing the intro. But let me know. So if you can hear us, say so. Oh, by the way, and hello if you can, and hello there, Landon. Hey, get it? Halo, halo. I got a halo on. We're talking about halos today. Yeah, no.
Yeah. Halo, and your radioactivity. So good morning, good afternoon, or good evening from your friendly secular astronomer. I say that depending upon your time zone and latitude.
And I wonder if I could actually still do the lead-in one because I mean I wrote that thing. I made that intro for the DEFCON 1 Science, but I don't know where I put it. So, oh well, you have to do without it this particular episode. But today we are going to be talking about polonium halos, and this was now all this stuff comes up here. Wasn't there before. So let me see if I can clear all this stuff out. Now I've got a bunch of grunge on my screen here. Oh my goodness. Just see here, Bob. I'll get rid of
But
that.
but have you been so far there? Have you recovered from your previous shows?
Um, Not quite. It's been a rough ride. We've been putting off, excuse me, we've been putting out a lot of content lately, and not just on our channel. I mean, we have obviously the non sequitur show that we're putting out content. Kyle does things with Hom and ideology. I've been doing some other things on this channel and some other channels. So yeah, we've been really busy, to
Yeah.
say the
And so
least.
it's been a bit busy for me. I was just previously on the Milwaukee Atheists. We were doing our Bible study, and they got me to read a chapter in Judges.
And how was that?
It was actually fun. We had a good because we have a good discussion. We read bits of it and we commentary and stuff. And it was all about Gideon and driving this stake through the guy's temple and good Christian values like.
Yeah, that sounds like good Christian values. I'm sure back then they did a lot of things that were probably not what a modern Christian would consider to be moral, because that was the time. But anyways, how do you want to do this? Do you want to like do the you want to like screen share the presentation, and I'm going to kind of go through it
Yeah,
and then let
yeah,
everybody know. This is a presentation I did ages ago. This was something that somebody had asked me to do that was talking about polonium halos because obviously this is something that comes up in the young earth creationist movement, and they wanted to really understand what the arguments were and why this was not a good argument. And so I did a PowerPoint presentation. The guy that actually asked me to do it just hand waved everything I wrote in this away, literally just by fiat, just dismissed it. So it has been a long time since I've looked at this. However, I think I remember enough about it to actually sound kind of cogent to give you guys a presentation on it and explain what the
yeah.
issues are.
And there's only one typo in it, so you get extra points if you can find the typo.
If not, I'll point out the typo. I mean, I made one mistake that I know I made a little minor error, but I corrected it. But the problem is I converted this to a PDF, and I don't think I have the original PowerPoint stuff that I can make it work, and so I can't go back and correct it. But I did note it. So
I have the power to edit PDFs in case you want me to
yeah,
fix
well,
it.
maybe I could. I guess I could do it as edible. not edible, but editable. There's a
Nom, nom,
difference
nom,
between
nom, nom,
edible
nom, nom.
and
Yes.
editable. Yeah,
Yeah.
that's a huge
I do not
difference.
recommend eating polonium. Yeah.
That would be bad for you.
Yes.
All right.
Even if you're a young person.
Yeah, well, what's worse, I just watched this video. I know we're a little off topic because that's what we do. But I just watched this video on a scientist that actually got exposed to 2 drops of organic mercury. And she didn't. She was doing an experiment, and she just in the latex. It actually permeated the latex. She actually died from it, but for a month or two, she didn't know what was going on. She had ataxic gait. She had peripheral problems. She didn't know what was going on, but she had a heavy metal in her system, and it was basically binding with other things and causing problems with her myelin sheath and for the neurons, and it was basically killing her. But by the time they found out what it was too late. It was a very disturbing story about how a scientist, got killed in doing research
But
because
she
she
decided
decided.
to say, well, the experiment, so let's just see what happens with the physical effects of it.
No, well, at that point, I think she was probably more concerned about last will and testament because it's certain things. I know they did chelation for her, which as a way of basically, if I correct me wrong, but a chelation therapy is where they add things to your body that actually would bond with the heavy element to try to
Yes.
remove it from bonding from something else, right?
Yeah.
Okay. But let's dive right into Polonium Halo. So
So I assume everyone can see the title slide on it.
yeah, and by the way, nobody told me if the audio is good because, like I said, I didn't even have our usual intro because somebody had something about the audio, and so I wasn't sure if it was bad or not. So I'm very paranoid on the audio because I tweak things all the time, and I want to make sure people can hear. So if you're in the live chat, let us know. They're talking about tennis in the live chat. That's how disinterested they are in this topic so far.
So is that because they can't hear us, or because
I,
let's see? Let me see if I can actually
No,
go
they can hear us
live.
because Smitty just said the woman who died made sure that her death led to better research in organic mercury safety. This is true. She did.
I can hear it on
Yeah,
here, so I will
yeah,
pause it there. So
that is true. She did do that. But it was
and
really
give
good
us a
stuff.
thumbs up in case you that helps us spread the word.
Like and subscribe. So let's dive into it. Polonium halos, what they are evidence for and what they're evidence for not. They are not evidence for a young Earth. This is kind of a primer on nuclear physics. We won't get too much into detail, but there is a little bit of math, a little bit of physics involved reasons. Because I think it helps to understand if you know what the physics are, then what's going on with these polonium halos. Because a lot of people have said, hey, young Earth creationists arguments say there's polonium halos and no such thing as polonium halos. Well, no, there are polonium halos. That's not the argument. They definitely do exist. So when you're out there saying no, polonium halos don't exist, it's young Earth creationist myth. No, they do exist. But this is going to explain what they really are and why that the person, Dr. Gentry, who made an argument that they seemed to indicate a young Earth, which, by the way, wasn't his actual argument. His argument that it seemed to indicate a Earth that was created very quickly, within a matter of minutes, not necessarily young. Okay,
All right. So
so
let me.
let's do this. And if you guys got questions in the live chat, please ask as we go along. So, Polonium Halos was made famous by a guy named Robert Gentry. He wrote a book called Life's Little Mysteries back, and I believe it was the 70s. And he was a nuclear physicist. He actually has an actual legit degree in nuclear physics. And he claimed that pleochroic halos, which are just discolorated halos, from radioactive decay in crystals, gave the appearance of different colors as viewed from different directions, could only have occurred during some kind of primordial or creation event, meaning that it was present when the Earth was formed, but it had to be formed very, very quickly, not over millions of years, but over a matter of minutes. And he took that and he ran with that to try to interpret that to mean that if it was going to be form, or Earth was going to form in a matter of minutes, that would be something miraculous. He actually, his word that he used was a singularity, one-time event from a deity that caused something to occur. Then that would be indicative or indicative of a young Earth. His reasons were based on the following: that polonium 238, which is an isotope of polonium, had a very short half life of 3 minutes and would have long decayed while this rock was cooling over millions of years because the rocks they were sampled, I believe, were about, they're a few hundred millions of years old, if I remember correctly. They were definitely very old, but they weren't technically primordial rocks, but they were definitely very old rocks. And his reasoning was such that when these halos that existed in there, the elements should have long since decayed. So there's no reason why over millions of years you should have these halos, because they do form relatively quickly. He also said there's no indications of apparent elements such as uranium in the sample material, and we're going to get into that. But basically, these halos from polonium come from the fact that uranium 238 decays. Also 235 decays. Uranium itself decays. And so in the decay chain, you have different steps, and you have different steps by what's called alpha and beta decay. Somewhere in that step is the element polonium, and there's different isotopes of polonium that produce different halos. He's arguing that there is no precursor, there is no parent isotope that he's seeing of these uranium halos that would lead eventually to the decay of various isotopes into polonium. So he's just saying that polonium was created in situ instantly, rather than over a period of time from a decay chain. That was Gentry's argument. And we'll get into why he thought that in the next couple slides.
Interesting argument. Okay.
Okay, so the arguments against his claim. Polonium is continually produced as a decay of radon gas, which is a radioactive gas, from decay modes of uranium. Okay, so it's not just something that's produced once and done. It's a continual production because the decay chains are continual. Uranium-238 is about 4.5 billion years, right? So over billions of years, a lot of decayed daughters are being produced. Granite rock produces large amounts of radon gas, which is easily diffused through these microfissures. Okay, there's also some other things that it can diffuse through. They're called whole cleavage plates, which are basically plates on a crystal that have slid, so you have a 90-degree incline and a smooth plane on it. That produces something that a gas can go through, or more likely, water seepage. So these were things that he didn't take into account, but they do exist in rocks. Halos can also be caused by. There's also some other things that it can diffuse through. I just started playing the video. Halos can also be caused by other elements other than polonium. We'll get into the different types of halos and how indistinguishable they are from other things. Gentry accepts uniformitarianism as opposed to catastrophism. Uniformitarianism is basically the idea that geological structures formed over many, many, many years, and there's a uniformity of structure such that if something is going to be this way, it's going to be the way it was yesterday. In other words, that the laws of physics don't change. If we see something like, for example, we'll be talking about what's called the law of inclusions, that law will hold true yesterday as it does today, as it is tomorrow. But the catastrophe view was that these granite structures, like mountains, were formed very cataclysmically, very quickly, like what you would see in the Bible narrative, right? Upheavals. But the uniformitarianism was no, they're gradual process over long periods of time due to plate tectonics. Would you agree with that, Landon?
Yes, and by the way, do you want to take questions that are in the chat?
Yeah. If they got questions, if we go for it.
So one thing is what I said asked about, you mentioned radon is what color does radon gas glow? By the way.
Well, you know what? I know that. Okay, I don't know the color because I haven't seen it. But what happens is when you have gas in a tube and you excite it with electricity going through it, they will actually have an ionized state in that gas that produces a specific color. I know,
like a neon sign.
Yeah, neon sign. Blue is oxygen. I remember that, but I don't remember what color radon is.
Radon is a really nice deep green.
It's deep green. Nice, okay, so kind of like this color.
Emerald green. Yeah. Yes, it's not. And the other thing is, wouldn't all radioactive glow be caused by shrink-off radiation?
No, Cherenkov radiation is when you actually have, in a medium like water, you'll have ionized charged particles traveling faster than the light traveling in the medium. Because you got to remember, the speed of light, c, is only in a vacuum. Light can actually slow down in various mediums, and how it does that is very complicated. But
that's diffraction, right? That's
it's like a sonic boom. The Cherenkov radiation is the light equivalent of a sonic boom, basically.
So it's charged particles moving through a dielectric faster than light propagates through that same dielectric.
Correct. Yes, and that produces the Cherenkov radiation.
Yeah, but you do not have Cherenkov radiation in a vacuum because there's no dielectric, and you can't go faster than the speed of light in vacuum,
Correct. So
according to the theory of
you're
relativity.
missing the dielectric, and you're missing the fact that you would have to have a charged particle going faster than c. That's not possible. So
Yeah.
okay.
Okay.
Um, so halos are microscopic and nearly impossible to resolve individual halos at even up to 1,000 magnification. Radon 222 and polonium 210 double halos appear, and they are actually nearly at the same energy level. They're only about 4% difference in energy level. So as we go through this, you'll see how energy levels affect the penetration power of the the alpha particles in the granite. So the higher penetration power, the further they're going to go in the granite. And since their energy levels are very, very similar, they're going to produce halos at the same position. Now you need a high resolution to determine which halo is caused by what isotope. And I'm going to show that Gentry didn't have the correct resolution to do that. He used what's called an ion probe and only had about 2 micron resolution. These things are less than 2 micron to resolve.
So asking, what is a halo?
We're gonna get into it. I'm gonna show you
So,
exactly. Yes.
pay attention.
This is just preliminary. We're going to be showing you exactly what halo is. And again, like I said, Gentry's method that he used to show these things can occur in experiments, he only used slow neutron tracks. Unfortunately, a lot of this is caused by fast neutron tracks and fast helium nuclei, which is basically an alpha particle or +2 helium nuclei. The probe that he used wasn't high enough to resolve these halos. So let's go ahead and jump right into it.
So let's what you just mentioned fast neutron and slow neutron. You should at least explain what we mean by that.
Slow neutron is called a thermal neutron. It's in other words when you have a target area. Let's say you have an atom and you have a neutron going by it. The slower the neutron, for certain atoms, like you say uranium-235, it likes to absorb slow neutrons. So the slower the neutron, the bigger target area. It's called a Barn ratio between the size of the target and the source. It is more likely to absorb it. Okay, there's nothing sexual by that, by the way. Don't get all dirty with me, people. But if it's fast, right, it's going to present a very small target area. So it's going to actually be less chance or less probable that it's going to absorb a fast neutron than it is a slow moving neutron for fission.
Yes.
Okay.
Yes. So some of it is a matter that you're nearby and there's a chance for absorption, and fast neutrons have less time to absorb if there's a probability of a certain period of time, where slow neutrons have a bigger chance of capture in some cases.
Yes. Okay, next slide. What are polonium halos? Polonium halos are visible defects. They're actually discolorations in a shell, which is going to be a three-dimensional sphere. Because you got to remember, you have a point we'll call the nucleation point. We're going to start with a little point. From that point, you have these particles coming out of it. Okay, alpha particles, beta particles, sometimes photons, but you have particles coming out, and they're going to be coming out in all directions. So this is actually a 3D model. So when you're talking about a halo, you're actually talking about a 3D thing, but you're taking a cross section of it. So when you're looking at like the biotite or granite, you're actually looking at a two-dimensional cross section of a three-dimensional object. So that's why it looks like circles.
Yes.
And that's where we're going to be when we show you pictures. It'll look like circles rather than a 3D sphere because you're just taking a cross section of the rock.
So one of the things when I was in college and I was attempting to try and see if I could disprove quantum mechanics, I was using halos inside cubic sulfate. So when a radon gas would decay to polonium and it would kick off a particle, you would get a defect that you could see under scanning micron, scope, whereas if the particle kicked out. So basically it's damage to the crystalline structure.
That's exactly what it is. It literally is. That's exactly what it is. It's damaging the crystalline structure.
And then so I was using that to say, I was wanting to prove that in this sample that had a very low amount of radium, that was decaying to radon, that was coming to polonium, that when I saw an electron go through a slit, only one particle decayed. And so I would scan the crystal and say, okay, there's a defect. That was a single event. I was trying to show whether or not electrons going through a double slit, where it was one electron at a time, was going to interfere with each other, which of course it was. So.
Yeah, I don't remember the name, but I have to look it up. There's actually a specific name for the energy required to actually take a atom and bounce it out of that crystal lattice and put it into a different energy level.
But a crystal's got this regular form, right? It's
yes.
like kicker toys with the sticks in them. and the wheels, so forth. And when you've got a charged particle moving through, you're messing up with those bonds and breaking things, and it doesn't reconnect back in a nice orderly fashion. And you can see
Yeah,
residual
it's called
effects.
interstitial point defect. Interstitial point defect would be where the lattice don't mix. So in other words, like everybody's seen like salt, right? You've seen the atoms, and then you have lines going through them with your bonds, and then so you have sodium and chlorine ionic bonded, but
Mm-hmm.
between between atoms themselves you have bonds, right? And those bonds in the crystal lattice is what holds that lattice together. And sometimes those bonds break, and then you have a shifting. And so, like the crystal would, instead of having a nice alignment of atoms, or have a shift. Those are point defects in there.
Yeah. Okay.
Okay. Um, let's see here. So let me go back. Here we go.
Here's a polonium has a half life.
Yeah. So, anyways, these are things that are found in mica, biotite, granite, fluorite, and also inclusions, which I'll explain inclusions here in a second. And radioactive impurities such as uranium and plutonium found in zircon, apatite, and titanitite. The what an inclusion is kind of simple. It's basically, and I hate geometry. I hate geology. See, I can't even pronounce it right. That's how bad I hate geology. Geology, I'm sorry, it's my weakest area. But an inclusion is basically a piece of material of some kind or mineral that is enclosed in a rock. In other words, it was there before the actual rock. So the law of inclusions would state that if you have granite and you have like sandstone on top of each other, and you have the sandstone specks in the granite, then the sandstone must have formed first. If you have the granite in the sandstone, then those inclusions means that the granite must have formed first. So that's how we can tell what formed
It
first.
moved into the other material,
It moved.
right?
It
Yeah.
moved into the other material. So it's just
It's not stuff escaping from the material to form a layer.
no,
It's the
no, no.
layer moves up into another thing, and so you'll see bits and pieces of the nearby layer working its way into, let's say, through pressure, through heating, through gas diffusion, whatever.
Exactly. So polonium 238, excuse me, 218 has a half-life of approximately 3 minutes and produces a charged particle called an alpha particle, which is the same thing as a helium nuclei with a +2 charge. So basically, that's just saying two protons, two neutrons. That's it. No electrons, because as you guys know, a neutral atom would be ones that have an equal amount of protons to equal amount of electrons. If you have a deficiency of electrons, you're going to have an overall net higher positive charge. Right? So an
Yeah.
He2 plus would just mean that you have a helium nuclei that has been ionized, missing two electrons. That's it. So this produces alpha particles of very high velocity and low penetrating power due to the very low macroscopic cross section for absorption on the target atoms. This is what I explained earlier. And the way that they figure this is you take the microscopic cross section for an individual atom, right? Let's say it would be the rock.
Mm-hmm.
And then you take it over the entire rock. So a microscopic cross-section absorption would be what you have for an individual atom, but the macroscopic would be over the entire distribution of the material. So it depends on your atomic number density and your microscopic cross-section of absorption. You just take the summation of that. That's going to give you overall how much penetrating power these helium nuclei are going to have in the granite and mica. And I'm going to explain where they get these, where Gentry got these numbers from.
Yeah. By the way, I should mention, you talk about this polonium. It's a radioactive material. I was first isolated, discovered by Curie and Marie Curie in 1898. And it wasn't until 1902 they actually got isolated enough of it to actually see that it was actually this, this nice silvery sort of metal there. But it's one of the it was one of the things that the Curies identified by pulling it out of essentially uranium deposits, isolating it chemically.
Okay. Next
Right?
slide. Okay. So the sigma, that fancy looking S, means summation. And one of these days, I think Landon and I, maybe we should do something along the lines of explaining what summations are. And maybe do sequences in series. I think that'd be fun. And people, I don't know. But anyways, it just means summation. It represents an entire effective target area of all the atoms present in the rock, which is the probability of an alpha particle from the decay of the polonium will strike an atom in the rock. So you take all the individual macroscopic cross sections. There is a microscopic cross section for scattering, which means what's the likelihood of something hitting it and scattering off. Radiative capture of an alpha particle, which, if I remember correctly, radiative capture.
Just the S thing is, if you look down in the
Yeah,
middle
down the
of
bottom
the
here.
slide, right? middle of the slide here. I don't think I can see the
You can see your
microscope.
mouse. Yes, yes, perfect.
Okay, so S is scattering. So this is about the cross section, the sum of all the atoms that could scatter a particle.
Yep.
Right. Keep
Yep.
going.
The next one is radiative capture. What a radiative capture is basically similar to absorption, but it's usually a non-fission event. So, and I don't know remember if it has to be a non-fission, but I'm pretty sure it's not. It's a non-fission event. So basically, a radiative capture is when the atom will absorb a neutron. It'll undergo excitation, but it usually produces a gamma ray which would be a photon, and then that lowers it down to ground state. So it doesn't fission, right? The A, the macroscopic cross section for absorption for would be what is the target size ratio? It's called a Barn ratio to the nucleus to the neutron that absorbs it and actually causes fission, and that would actually destroy the original parent isotope. So this is actually saying for the nuclei what's happening as across the entire granite structure as a macroscopic cross section. What's the likelihood of an alpha particle interacting with something in the granite? This is what that formula would look like. And by the way, I pieced these formulas together. You probably weren't going to find them out there somewhere. This is what I remember from nuke school. This is all stuff is literally taught in naval nuclear power school. So I'm drawing on old information here, but I'm pretty sure that this formula there is something out there on it because I remember.
But basically, it's saying that the cross section is a sum of scattering, things bouncing around, things being captured, and things being absorbed.
Yes. Yep, exactly. So basically, this is based upon the number of atoms in the rocks and the atomic number density. So that's basically
all
it.
right.
All right, next.
Next.
Threshold displacement energy. That's Freno says. That's kind of I think what I was referring to. There's actually a name for that threshold displacement energy. There's an actual name. I think it starts with a G. It's not Gibbs, by the way, but it starts with a G. That actually is the energy required to displace an atom from the lattice to have it go down to a lower energy level. But I can't remember what the name is called. It's been too long. Forgive me. Hang on. All right, now we get into some good math. The average logarithmic energy decrement per collision coefficient. Also, you may find this like on Wiki. They don't call it that, so you're not going to find this too many places. This is literally what they called it in nuke school, but it's called the lethargy gain per scattering event, which basically means per event how much energy is reduced. And it's that squiggle sign. I believe it's the Greek letter xi. We pronounced it squiggle. Is it Xi? Chi? How do you pronounce XI? I don't even know. We never actually pronounced it. We just call it squiggle. But squiggle is the average energy difference between the logarithm of the energy and the logarithm of the energy after the event, basically. So it's the energy loss per scatter. The whole equation is basically the total energy loss is the summation. All the atoms in the granite, based upon the nuclei density, the macroscopic cross sections or the microscopic cross sections for absorption, and then how much energy is lost per event. So basically, this is a ratio. That's all it is. So it's just saying, here's the energy loss. What's my ratio? That's the average amount of energy across the system that's lost as a whole by all these scattering, adaptive radiation, absorption events that are all added together. Okay.
Yeah. All right. Yeah. So that's right here. Yep. Next slide.
Next slide. All right. There's something also called the mean free path. And when the mean free path is basically what path average does a particle take through a medium? Does it go in a straight line? Does it go do? What is it? The path? And an alpha particle, how it penetrates the rock, how it interacts with the atoms, is the total sum of all the macroscopic cross sections of the rock material. So if it's made out of biotite, if it's made out of apatite, whatever it's made out of, it's going to be made out of multiple things. So the mean free path is going to be based upon the summation of all those different types of rocks, microscopic cross sections for absorption. Actually, it's going to be there. Rocks macroscopic cross sections for absorptions. You guys try saying this 5 times fast, okay?
Yeah.
Yeah.
But people are also saying that it has a KS sound. So KSI would be the how you pronounce.
Because Zai, I think it's Zai, Zus.
Yeah.
That's why we called it squiggle. Nobody even knew, and I don't speak Greek. So this would be the gamma. This is where the gamma. And again, gamma is used for a lot of things. Gamma is one of those symbols that's used for a crap ton of things. So don't when you see gamma, you go figure out what it's going to be used for because it could mean
Yeah.
a lot of things. Trust me.
So for example, mean free path in nuclear weapons, this would be the sphere radius, right? That is the amount of material you need to have physical material around. So you have the mean free path of a neutron before it gets absorbed. You need to have a ball big enough that the neutron has a reasonable chance of hitting something.
Yeah, because I mean, you have to have it penetrate so far to actually hit something, and then when it hits something, that's when it stops that path. And so, literally, if you do what's called quantitative analysis, if I look at this formula and I have one over something, if the denominator goes up, then you by what's called quantitative analysis, the other side of the equal sign has to go down if you're in equilibrium. So the more material you have, the higher the density of the macroscopic cross sections combined, the summation of that, the shorter the mean free path. Okay, it's basically just basic math. The
Yeah.
more material you have, the shorter the path. The less material you have, the greater the path. It's kind of common sense. Okay. Okay.
Yeah.
Next.
Yeah. And by the way, it's critical mass is under the current conditions. Bayes' theory of critical mass says how much material do you have to have in an uncompressed form to sustain a chain reaction.
Yes. All right. Out of a particle lost, produce a halo. Here's some things to note. Again, we will get to the halos. The only significant mechanism from our energy lost in this system is the fact that because you have electrons in the medium, in the rocks, being absorbed by the helium nuclei. Because what's going to happen is that helium nuclei has a +2 charge. It's going to actually want to gain electrons to become neutral. Okay, so
Yeah.
that actual process causes an energy loss. It causes it to slow down. Also, very slow speeds, nuclear collisions occur. So, in other words, the slower the particle, the more collisions, and so you have energy loss because it's slow. And the fact that only a small amount of energy is actually transferred amount for each interaction. So these are some key points to note of why these halos are produced exactly the way they are. Um, and because you have a very high charge, +2 is a pretty good decent charge, and low velocity, the path is pretty straight. Okay, now there's that mean free path that we can have like this. Imagine like a Plinko machine, right? You have a ball dropping, and it goes this way and that way and this way. That's like a mean free path. And so this is actually pretty straight because it's very high charge, very low velocity, and there's very low energy loss per collision. Okay, and it's continuous. It's constant. I mean, it's always slowing down. It'd be a linear function that is going to be slowing down its velocity rather than something along these lines.
All right.
Okay.
Next.
Yep. Now we have a halo. Okay. So this is actually a cross section of a halo. As you can see, this is literally half of what you would have for a sphere. And if you just looked at the circles, right? If you just took a two-dimensional cross section of it, that's the halos that Gentry is referring to. So when we're talking about polonium halos, we're talking about the whole thing, but we're really more concerned just about the two-dimensional representation because that's what he actually was taking pictures of. You can't really photograph the whole sphere of any reasonable means, but you can do it as a cross section, right? So we have a radio center, which I tend to call the nucleation point, which I don't think is unreasonable, but I don't know if he uses that. I do because it is a nucleation point.
It's the place where the particle came out.
Yeah.
It's a polonium atom decayed at that spot. That's what you're talking about.
Exactly. And so you have all these alpha particles coming out from that center. And they're all going to be at different energy levels. But for each isotope, you're going to have an average amount per isotope for energy, right? So it's going to produce some that go shorter, some that go latter, further. But overall, you're going to get a nice area, a region, a range of where you're going to have that particle be absorbed. Okay, so let's have a range. You have the inner and the outer, and then you're going to have the medium. Okay, that's what actually produces that sphere or that circle that you're looking at.
So if you have polonium, 218, you're going to have a different energy, decay than polonium 210 than polonium, 214, for example. So you will see that the inner area, polonium 210, as only 5.3 million electron volts. What do I mean by that? The energy of that particle coming out is energy equivalent of essentially an electron across a potential of 5.3 million volts.
Exactly. An electron volt is how much is required to move one electron, the amount of energy required to move one electron through a potential of 1 volt.
Yeah.
It's
So
the
a
energy
5.3
given.
million gap would give you that. So you notice that the energy of the 5.3 million has a sphere that's a certain radius. The 6 million electron volts is a little bit larger. The 7.8, 7.69 is even larger.
Yeah. Technically, if you want to get to electron volt, would be how much energy is required to accelerate an
Accelerate an
electron
electron
in a
through a
potential field
potential
of
of
one
one
volt.
one volt.
Exactly. That's if you
Yeah,
really want to get pedantic.
yeah,
Um,
yeah.
so um, this is going to be how much of the uranium, excuse me, the plutonium 218 is actually due to alpha decay, how much is due to beta decay. The difference is alpha decay, as we discussed, is your helium nucleus. And by the way, we have a guy that's in the live chat that actually wants to be a particle physicist. Pay attention. You're going to be knowing this stuff in your sleep. This is like first year stuff. Actually, it gets complicated. It gets worse. Trust me. Um, so only 0.02% is beta decay. That's electron. So when you see beta decay, you know they're talking about a electron being produced. And if I say anti beta decay, what do you think that's going to be? Landon, tell them what anti beta decay is.
Positron, right?
Positron or
So
positive
what you
electron.
really have is in the nucleus you have a neutron that is turning into a proton by kicking out an electron and a antineutrino.
Electron antineutrino.
Yes, yeah, electron antineutrino. So
Yeah. So a typical beta decay would be something along the lines of a proton going to a neutron, going to an electron, going to a um, anti neutrino electron, and there's different types of neutrinos. So there's electron, tau, and what's the other? Tau, electron, and muon. And
mu, yeah,
yeah, a muon. And there's the reason why that has to be produced is to various reasons. One of which is energy conservation. They noticed when they were looking at these decays, energy was not being conserved, and they said, okay, some particle has to carry it away, and that's how they predicted, right, because of the model, that they should have another particle. And then they detected the
yeah.
neutrino, and also that it's anti for conservation of there's like
And
lepton conservation, baron conservation. There's a very conservation
very
laws.
covered people like Pauli and Fermi that did a lot of work on that. But anyway, the point here is that there's various types of decay. What he's talking about, beta decay, is usually in the nucleus a proton, a neutron converting into a proton by kicking out an electron.
Right.
That's the beta particle. The other type of decay is where the nucleus sends out a pair of neutrons and protons bound together, a helium nuclei, if you will, that gets kicked out.
Two proton, two neutron.
Yeah, two proton, two
Yeah.
neutron.
Okay. And so the way this is what we call a decay constant. A decay constant, contrary to what young Earth creationists tell you, is a constant. That's why they call it a
A
constant.
constant.
There's a reason why they call things constants, right? Go figure. And the way that's basically figured is basically taking the natural logarithm of 2, which is ideally points. I'm going back here. I haven't looked at this up. Is 0.693 mathematician guy
Yeah,
somewhere in
yeah.
the? I mean, it's been a while, but nobody goes by that. They just say ln2, but I believe it's point six nine
But
three.
but but if you're talking about it, it's 0.693.
Okay, so I was right. Hey, that going
One.
back a few
Yeah.
years. So ln2 divided
Da, da,
by.
da, da, da. It's going forever, but yes.
Oh yeah, obviously. But I mean, let me round, okay?
Yeah.
Um, so you take the ln2 and then you just divide it by the half life, right? So half life is how much material has gone from t0 to t1. So if I
So
have
there's Helen 2 and there's a half-life here.
yep, if I have
That's
1 gram, then a half life if it has a half life of 1 second. In 1 second, half that gram's gone. So I have 500 milligrams, right?
Yep.
Right. So that formula, that ln2 divided by the half life, will give you a specific number in minutes raised to the -1, which just means 1 over, right? So negative
Yeah.
one,
So
1 over.
so this per minute really is what you're talking
That's all
about.
it means, right? So that would
Log
be our
2
average.
per, yeah, yeah. Yep.
That we can actually use to find the average mean lifetime. And what we mean by that is how long is that particle expected to live? and we use tau for that. And tau is based upon the half life over natural 2 logarithm 2. It's basically the reciprocal of the decay constant for all practical purposes,
Yeah.
right? I mean, look at it, you can tell it's reciprocal. So we would expect in 4.472 minutes, that would be the average length or time for a particle to exist.
Yeah. Yeah. So if you it basically it's this formula where you're solving for t rather than solving for lambda. Yeah.
So basically, by doing all this math, you come up with the fact that your half life is basically your tau times ln2, which is 3.1 minute. That's the decay half life of polonium 210. So there, that's all that is. So next. But you can see here that different energy levels will give you different size halos, right? More
Yeah.
penetrating power. Okay.
And hello, Gage, and hello, Raisin.
Hey, Gage. Hi, Raisin in the live chat. My mods. How are you guys? So this is going to be basically where we. This is about as much as the math it gets to. Don't worry. I don't think there's any more math after this. But I think it is important to understand how we derive these formulas, because if you're going to learn about polonium halos, you've got to understand radioactivity. So the exponential decay for radioactivity can be expressed in a first order differential equation. And first order just means first derivative. Okay, there's second order derivative equations. But a first order is just a first derivative, and it's based upon the negative decay constant times the number of atoms, okay, assuming
Yeah.
that the decay constant is greater than 0.
Yeah.
Okay, so when you see dn over dt, that means time rate of change. And I'm going to be dumbing this down a lot. We have a mathematician here that can explain it epically because he's one of the best mathematicians in the world. But I'm doing this only because I'm a layperson, and hopefully I can dumb it down to the point where you guys get it, because I'm dumb on this.
And the pedantic details of math are not important to the story at this point.
I hope not, because I mean, obviously I took a lot of calc, but it's been a lot of years. But anyways, so a dn over dt would be the time rate of change of the number of atoms with respect to time. Okay,
Mhm.
so we want to solve for what's called a general solution to that differential equation. Now again, differential equations you don't really get into in first year calc. You start getting into and later on, but it's good to have an understanding what differential calc is, even from a basic calc point of view, if you start doing derivatives. So I want to solve this differential equation. And many of you guys probably never solved a differential equation before. This is one of the easiest ones to. There's only one I can think of that's easier to solve than this one, and I believe it's negative y over x.
But you're saying what function will give you this derivative?
Yeah, I want to find a general solution set of what function is going to give me this derivative, right? Because I'm working backwards.
And what is a derivative? It's a rate. It's a rate, right? If you will.
Time rate of change. Yes.
And why are we doing that? Because decay has a rate, right? So we're saying what function is going to give us this kind of decay?
Perfect. Yeah. Yeah. Exactly. Because I know the rate, right? Now I want to find the function that corresponds to that rate.
Yeah.
So
remember back here the rate was done by this, right? By this constant. So now we say what function gives us that thing. So
okay, so now I set up the general solution, and I kind of just rearrange it a little bit. And the way the way you do that is the dt. Think of it as a combined thing. It's not two symbols. It's not d times t. Okay, this is where people that haven't experienced calc forget your algebra crap. dt is one symbol. It means a differential.
Just like dn is one symbol.
One symbol. Right? It's not d times n. It's not d times t. It's dn over dt. Okay, so don't think like I have dn over n. I can cross those n's out. It doesn't work that way.
Or the d's out. Yes.
They don't cancel. Yeah. I can't cancel the d's out. So I move the differential to the other side. So now I'm left with dn over n with respect to dt. And there's a reason why there's an n there, right?
So all you've done is basically just thrown this n under here.
Yeah, I just moved this over here, and I move the n on the other side.
Yeah, so we would swap these two, right? That's from here to here, right?
But don't cancel them. Don't cancel them. Okay.
Yeah, don't cancel.
Okay. So okay.
And then you can integrate both sides.
And now I can integrate. So when I integrate, right, integration is the opposite of doing a derivative. So if you don't know the rules for integration, it would be very difficult. But I can tell you right now, for the left-hand side, this is actually, and before you integrate, I actually separated out the one end to make it easier. Okay. Yeah. So basically, the dn over n is the same thing as saying 1 over n with respect to n. Right? That's exactly the same thing. I'm just moving it out of that I'm taking one. I'm taking a one from the top because one times anything on the top is still one. So I'm taking a one from the top, and then I'm just moving the n out. So it's one over n with respect or times dn equals the integration of negative lambda
Okay.
dt. Okay.
Okay. Again, folks, you have this. You have this equation where we move the n on this side and dt on this side. We integrated both sides, and we pull the one over n out so that we have one over n times dn.
Yeah, I will
Right.
never make it as a math tutor. Okay, I understand
Right.
halos, but math. All right, so now we actually want to do the integration, and Landon and
And
I
you
both
know,
know that what's the integration of anything over one over something?
a lot. It's log that something, right?
It's natural
So
log that, right? So
yeah.
go ahead.
So you're basically basically we solve basically iterated both sides on here.
So I'm ending up with natural log n because that I've done the integration. So the integration of 1 over n is natural log n, and on the other side, okay, I have that's all constant, right?
Yeah.
Okay, so I'm basically just taking negative lambda t now, but I have to add in what's called a coefficient of integration to get a general
Yeah.
solution,
Plus C, right?
which is plus c.
Um,
You
you
can
know,
explain that probably a lot better than I can.
yeah. But it is yeah, I remember the old adage of the integral of what are in dn is log n plus c, which is how like log n log
Log
plus
in,
c.
yeah, I get it.
Yeah. C Costco. Okay. Yes. That's how I remember that.
Now, when I learned DiffyQ and calc a little bit, we were forced to have C1 on the left hand side and C2, and it didn't really matter, but you had to have C on one side and C on the other side, C1, C2. Then you combine that into CT, C total. Now I
Yeah.
understand there's no reason to do that, obviously, right? But it was just to get us to understand that each side has a constant,
SSD.
right?
Yeah.
So
And
when I
so it
integrate,
is.
well, real quick, when
Yeah.
I integrate integration dn over n, I'm actually getting ln plus c, right?
Yes. So there's a constant here and constant here. What we've done is just move the constants to one side.
We just combine them and call it c, right?
Yeah.
So, and by the way, my little math error here is
Right there.
when you can raise all this stuff to e, okay? Because e ln n equals e negative lambda t times e to the c. I forgot that
That's
negative
it.
sign. And as anybody who's
That's
ever watched my stuff knows, in nuke school, I told them I had a hell of a time with minus signs. This is
Yeah.
exactly what I would do. I would do shit like this and
Yeah.
forget the minus sign.
So there's a little minus sign right there, but pretend there's a
Yeah,
minus sign there.
there's a little minus sign there. So basically, this is you can actually do this in calculus. If I have ln e, or some ln on one side and something else, I can just raise it all and put that as the exponent to e. And I have a video on the Great Debate Community channel why we could do stuff like that. E is really cool. I took the derivative of e to the x. Why the derivative of e to the x happens to be e to the x.
Yeah.
It's weird, but yes, the derivative of e to
Yeah.
the x is e
Hang
to the
on,
x.
folks. It'll get easier. No,
No, it
no.
doesn't. It doesn't. But anyways, so long story short, by getting this differential equation solved at the initial point of time 0, e to the c is just a constant. So that's just equal to c at t equals 0. So I can eliminate that. And I'm left with this formula, which you guys have all seen before. It's called the PERT formula. P equals E or T, right? They call it PERT. It's the same thing. NT is equal to N initial times E raised to gamma times T. And you guys all worked, anybody who's worked in any kind of basic physics or had high school physics, you've seen this formula before for
Yeah, because you're
exponential
using
decay.
you're using gamma here. We've also done you just sometimes use
RT,
lambda, but
you,
but
yeah,
but but basically the number over time is the initial amount times e to a negative value that is an exponential decay, right? This is
yes.
the that so the lambda here the gamma is your decay rate over time. So you start with initial value and it's going to decay exponentially decay over time.
This is how you get that formula from differential equations. So okay,
Yeah.
next. All right. So comparing the different isotope penetrating power, if you look at, and this is from Gentry's work, if I remember correctly. I believe I did get this from Gentry's work directly from this book. But if you're looking, imagine this as a cross section. Then each of one of these halos represents a small arc of a circle that's representative of the entire sphere. So the inner one, if you look at it, is uranium-238. That's the energy level, the penetrating power to go that far in the material. Then you have U-234, U-230, thorium-230. And I'll show you the decay chain. But all these isotopes, these nuclides are in that decay chain for uranium-238. So each one that produces either a beta decay or alpha decay is going to produce a halo. Now the alpha decays will produce a much greater halo. I'll explain why coming up. But that's why you mostly just see these. We're only dealing with alpha right now. Don't really worry about the beta. But these are all due to alpha particles being emitted from that center. And so the if you put in the first quadrant, can you hover over the first quadrant where it has all the ones? Yeah. So this is what it looks like as a whole. But as you start eliminating some of them, and if you move to the fourth quadrant, if I remember correctly, it goes 1, 2, 3, 4, right?
Hmm?
Remember my geometry. So in the fourth quadrant, where it has polonium 218. Wait, that's the second quadrant, isn't it? Doesn't it go 1, 2, 3, 3, 4 for quadrants?
Don't you go from one?
I don't
If you
remember my
go,
geometry. I thought it was
if you go
quadrant one,
from this one,
quadrant
two,
two.
three, four, like this, yeah.
Somebody have to remind me. I'm not going to look it up. I thought it goes quadrant
Because,
one, quadrant
because
two.
you're reducing your set down, right? If you look at this,
All right, so it goes 1, 2, 3. Oh, you know what? Now it bugs me. I gotta know. This is like basic geometry. I don't remember. Oh
right?
my god.
Because theta starts off your angle starts off at zero, and it
Yeah, but
goes to
doesn't it go
90
this way?
degrees, 180 degrees, right? It's counterclockwise.
Um, you're right. So it goes 1, 2, 3, 4. Okay,
Yeah.
that's why he's a brilliant mathematician, and I suck at geometry.
Well, I
Yeah,
just
you're
remember
right.
some things.
Yeah, you're right. It's
I
quadrant one,
haven't
quadrant
forgotten
two, three, and
enough
four.
stuff but yes, okay.
Okay.
So one, two, and you look, you basically you're doing reduction down here. So
All
yes,
right. So moving to the second quadrant, the polonium halos you can actually stand out more. So 210 and 214 are pretty close to each other. Are pretty close to each other. But
Mhm.
218 is a lot further out.
Yeah.
Now this is
But again, the
highly
energy level,
magnified. Highly magnified. You
right?
actually see when we get further that 210 and 214 are
You see these energy levels are different. Yeah.
they're
Okay.
yeah. Matter of fact, if you look to the if you look to the next picture over to the right, the whole thing, yeah.
Mhm.
Look at the 210 and 22 radon 222. Look how close they are. They're literally indistinguishable from each other without very high magnification. This is why Gentry is calling these polonium halos and not radon halos, because he's just assuming that there's one circle there, and we're going to get into that why that's significant. Okay, so next, Gentry based a lot of his numbers on this formula here, and this is how much in air, dry air at standard STP, the range an alpha particle will penetrate.
Air as in stuff you breathe, not error as in
Yeah, air.
error. Yeah.
So in a free space, air, um, where R is in centimeters, where the energy level is less than 4 megaelectron volts, that's the amount of energy. I mean, so that's the amount of centimeters per energy level we should see.
So
And
you're saying it's something that's roughly 4 millielectron volts. It'll move roughly in air.
if it's 1 megaelectron volts times 50.56, just be 0.56 centimeters.
Yeah.
Okay. Now, if you kind of go through this will come to about 4.19 centimeters. I'm not going to go through all this math because it's not that
Yeah.
relevant. But
Well, what does it mean? It means that if you are 4.19 centimeters for those that are metrically challenged, it's roughly about an inch and a quarter, something like that. Inch and a third, right?
Yep.
So I mean, if you are an inch and a third away from this radioactive particle in air, is it you have a half chance of being detected, or it will?
Well, no, this is just the penetrating power. If I have an alpha
Okay,
particle in
okay,
air, how
yeah,
far it's going to go? It's going about
yeah.
four
So
centimeters. Okay,
so in
not
other
so
words,
big.
you can be an inch and a half away from something that's at that energy level.
It will never touch you.
Yeah.
Yeah. Okay, but this again, this is legit, right? This is actually from a study. I don't remember the paper I got it from, but this is a legit number. But it's only for range and air. Okay, so next thing. Um, how can alpha particles emissions result in discrete colored rings? Gentry's thing in 1992, he claimed that these pleochroic rings are formed because the alpha particles do the most damage at the end of their paths. Okay, which is
Hmm.
based upon the stopping power of the ionization particles in a medium and is reference to the Bragg effect, which I will explain. But this is critical because he's basing it upon that formula we just had before. He's saying that because of 4 centimeters, his math would be that he would expect in biotite, in granite, that the halos that are produced is what we would expect because alpha particles do the most damage towards the end of their path, and I'll explain why here in a minute. But he gave no reasons why um, beta particles couldn't cause some of the halos that he did. He just discounted those, and we are as well, so I don't want to get into that too much. But he 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 based that upon the stopping power in free space. This is not in free space. This is in a medium of rock, and the Bragg effect, which basically is as a particle moves through a material, it starts to ionize the nucleus would be the helium nucleus, and so it gets less ionization potential. It slows down. It interacts quickly with other things in the rock because it's slower. It becomes even more neutral because it's absorbing neutrons. It absorbs the first one, it slows down. It absorbs the second one. As it slows down, there's a higher chance of absorbing neutrons. So at the very end, it's going really slow, right, and doing a lot of damage because just before
Yeah.
it gets to a neutral state, it is still ionized. It's slowing down. Then it's. I mean, I'll go to the next thing. I actually have a picture of it.
Yeah. By the way, when you're talking about air, we're talking about dry air. We're not talking about where it has lots of
Yes,
water
it's
vapor.
dry STP, standard temperature pressure.
Yeah.
So this is actually the Bragg effect. This is the stopping power of alpha particles um, in centimeters. So what happens is the now picture this: you have an alpha particle which is positively charged by 2. It starts the mean free path. This is what all comes together. It starts this down this mean free path, and as it does, it starts interacting with other atoms based on the macroscopic cross section of all the materials in that medium. As it does that, it slows down. As it slows down, this is a highly likely it has more of a chance to gain an electron. So at about 3 centimeters, 2.5 to 3 centimeters, you look at that slope. Okay, what's happening there is it's becoming very slow. It's doing a lot of damage because it's spending more time next to other things, and then it absorbs an electron, and then it absorbs another electron, doing damage because it's absorbing electrons from the material. That's causing damage to the material as well, and then it becomes electrically neutral, and then it doesn't interact as much, and then the velocity tapers off. So
No.
that's that Bragg peak right there would be when it's neutral. So you have an ionized particle. It's doing damage. It's doing damage, but it's ionized now, and then it just falls off. Okay.
All right.
Want to add to that?
But I think basically again, remember that these alpha particles, these the helium nuclei, um, when they've absorbed 2 electrons, they're just now helium, right? Moving, and that's going to not. It's not going to interact
Right.
chemically, nor is it going to interact with charged particles because it's now a neutral atom.
It's a nerd at that point.
Yeah, and that's what this dropping off to stopping power to because now it's just
Now I looked at the stopping power formulas. We didn't learn the I think it's pronounced Beth formula. I think it's Beth. But those
yeah.
formulas that really get into how these things actually interact, way beyond my pay grade. So I didn't bother to include it, but if somebody wanted to go check it out, I just said it's too complex to go into because even I didn't understand it. The
Oh,
equation there I understood the stopping power, but that's about it. So
yeah. Okay.
all right. So Gentry's experiments. What he wanted to do, he wanted to duplicate these experiments to show that these halos were caused by alpha particles during the formation of the Earth. Okay. He had some problems because he tried using helium ion beams. He couldn't duplicate the same amount of damage, and he couldn't duplicate the discoloration, the pleochoric discoloration. There's 2 main reasons for that. One, the speeds. Okay, these were actually beams. He had very little control. And two, more importantly, these halos are actually produced over very long periods of time. Okay, he had to do it very quickly. He wanted to show that they could form very rapidly because that was his whole hypothesis that the Earth formed very quickly, cooled down very quickly, and just kind of as these radioactive things were decaying, the rock solidified around them, showing that that creation happened very fast. And then he just kind of somehow related that to young Earth creationism. I've never figured out how he did that, how he got from, oh, it was fast, ergo 7,000 years. There's just a disconnect between those two, but he did it anyways. Um, Short-term exposure to an ion beam can create damage equivalent to millions of years of low-level natural alpha radiation. Okay, but it didn't produce the in situ, which is means on in the system, right on site. Um, how do you explain in situ? In other words, not in the lab, in situ of the rock as is, right?
Yeah.
It didn't produce the discoloration patterns that we were trying to that we saw, so it didn't emulate it exactly. He failed in that regard. Um, and the conclusion basically is that the ionized alpha particle bombardments disrupt, as Landon pointed out, the crystallinity of the what's called the terminal material, physically changing the properties of that crystal lattice as the particles move through it based upon the Bragg effect. But the discoloration only occurs for very, very technical reasons that I don't even know because I couldn't understand it when I looked into this. Um, that it would have to be over a long period of time. It would not happen just with a helium ion beam. Okay, so his own experiments failed to produce or replicate something that would support his hypothesis, or more importantly, reject the null hypothesis. He was not able to
Yeah.
reject the null.
Yeah.
Assumptions made by Gentry was that much of his work was done by a professor of Trinity College named John Joly. Joly made very speculative assumptions of alpha particles only travel about 3 to 7 centimeters in air, which we had brought up earlier. That was the range, 4 centimeters or so. Then that means they could only travel 1/2000th of a distance in biotite. So what he did was he took the range of free space for polonium 238, and he said, okay,
210.
well, in this particular case, it was 218 that he was working with. I remember. Well,
Okay,
no,
two
it could have been two. Well, it was polonium. Let's just say polonium. I could have made a mistake. It
Yeah.
could be 210.
Yeah.
Um, but the 4.8 centimeters divided by his conversion factor for how much it would be if this in air, how much in rock, gave him about 20.9 micrometers in biotite. The problem with this was he pulled this number out of his ass. I couldn't find anything, and I did this presentation 2 years ago. I looked, I couldn't find anything to substantiate where he got that 1/2000 from. It just
It was
he just made a
a
speculative assumption.
yeah, made an expected guess.
Yep, and that's fine if you want to make speculative assumptions. I get that, but Gentry, and by the way, Professor Jolly is a legit scientist, but Gentry took that and ran with it to make that say, okay, this is what we'd expect to see as a halo based upon this purely speculative assumption.
I mean, what he could have been saying is let's presume for the sake of argument that it's 1/2000th out of air. He's doing like a back of the envelope calculation, not trying to state, I measured it this way.
Yeah, and I think I found out later that this actually speculative assumption was completely in error. So trying to catch up on that. Anybody in the live chat caught up? You need any questions so far? We losing you? You guys understanding this? Okay. Next slide. So this is actually from an actual publication. This is actually showing the relationship between polonium 210, the disk, which is if you look at the cross section, you're going to see a darker area in the middle. Okay. Then you're going to see rings, and so that rings is a combination of multiple rings, and it shows the outer ring, the inner ring, and all these were the micrometer readings of very high magnification of where we'd expect these rings to lie. What range? From the inner part of the ring to the outer part of the ring. And if you look very closely, the inner ring on the second ring was 20.9 nanometers, right? Or microns, micrometers. So that was what Gentry, was trying to go for, right? Obviously. So this is something that leading him to believe that his own hypotheses. But the problem that he ran into was if you also look very closely, the other rings also fall in a 2 micrometer error or measurement. So 20 plus 9 plus 2 is 22.9, but the first ring is 19.3. And so if 20.9
Yeah.
minus would be 18.9, The
Yeah,
first and second ring are indistinguishable from each other for the most part.
because this is your error
That's your error for at that
right.
resolution.
And so it's here versus this and this. You're not going to see. Yes. Okay.
The inner and the outer, like the 20.9. If you add 2 nanometer resolution, you're gonna have 22.9. So the outer region, 23.1, is actually point 0.2. You can see, you can theoretically see that because it's a little bit greater than your resolution. But if you're having two rings and they're less than 2 microns separable from each other, you can't resolve that.
Yeah. These two are within the same.
Right, the maximum, the inner rings, the first rings, the whole thing's for the 210 and the part of the 214 ring, they're indistinguishable from each other. And also with the radon ring, the radon 222 ring is indistinguishable from one of the polonium rings. And that's going to be a primary consideration because, as we find out, I'm a spoiler for you, radon is the explanation of why we actually see these rings, where we see them, and that nullifies this hypothesis. So, next slide. Um, I'm not sure why I added this. Gentry concluded that did not exist or was not in minute quantities and inclusions. I'm not sure why I added that. I don't remember. So it's been a while since I've done the presentation, but I know he didn't take into account inclusions. But inclusions are about two nanometer, and so the inclusions might have had polonium in them without a parent isotope like uranium. I think that's why I added it. But we're going to find out that there is a parent isotope. Because again, you guys remember, we should see uranium halo. Inside that, we should see thorium. We should see
Sure.
polonium. We should see radon. We should all these halos together because they're different energy levels from a central nucleation point or radio center.
Yes.
But
Where thing is decaying, and the daughter particles are also having their decay products being kicked off.
right, and what he saw was separate of that. He just saw the polonium halos. So instead of seeing with a nice concentric thing, all he saw was polonium halos with no parent isotopes around it, no halos from uranium. He said, "Oh, this polonium must have produced in situ, in creation, all at once." God said, "Poof, exist." So he didn't take into account two factors. One, that polonium could have come from inclusions, and it could have came from what's going to find out to be radon 222.
All right. So
Um,
next.
okay, so this is the decay chain. You start with uranium 238. It has a
Right
half
here.
life of 4.5 billion years. Okay, long time. And if you don't know how to read a decay chain, basically it's just saying that uranium is going to turn to thorium. Okay,
Right
and
here.
it's going to do through a process of alpha emission, which we determined is alpha decay.
Yep. And at 27 days.
Go to protactium. Pro, oh, I hate this one. Protactisium. Is that how you pronounce it?
Yeah. Protect.
Yeah,
Yes.
protactisium. Some of these words, who creates these things, right? But protactisium only has about a minute of a life expectancy. Okay, so that's going to undergo beta decay, which is an electron. That's going to form uranium 234, right?
Mm-hmm.
That one has a 250 some odd year life expectancy. That forms thorium.
250,000, 245,000
200,
years.
200, yeah, it's 245,000
Yeah.
years. So in 245,000 years, half of it's going to decay. So this is a long period of time we're talking about here. Okay, thorium, and then you see radium, and then we get to radon 222.
Yeah.
Radon is 3.8 days. Now, his reasoning was, I mean, he knew about radon. I mean, he's a real physicist. But his reasoning was that if it's only 3.5 days, it's not going to really migrate anywhere. I mean, it's not going to go. It's not going to do much in 3.8 days. So we should still see radon, radium, thorium, uranium, all in one. Like think of the nested
Yeah.
eggs for like Russian dolls, right? These all should be nested in each other. We don't see that.
So once from a geological point of view, once uranium 238 decays, it's a matter of days and minutes to get to uranium 234, which is around 250,000 years, and then it will go to thorium, which is around 75,000 years, and then you'll get this rapid decay.
And this is all a continuous process. This doesn't stop. As
Yeah.
long as you're uranium, you'll have certain amounts of isotopes being produced, right? And then if you look, you have three different types of isotopes of polonium. You have the 218, 214, 218, and those are usually through a lead chain You have lead and bismuth, lead bismuth. You've also got some thallium, and you also got some mercury involved. But eventually, through some type of decay, alpha or beta, you're going to end up with either um, well, actually, it's eventually all going to go to uranium polonium 210. That's going to go to lead 206. That's going to go to thallium 208. No, wait.
No,
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 no. I'm sorry.
lead 206 is the end.
Lead is the end. So you're gonna yeah. So you have 210 to lead, or you can have other decay chains where you go through mercury to thallium, thallium to lead. So the lead 206 is going to be the end result of all this at some point. That's why when you find lead, you're done. That's the end of the decay chain. Lead doesn't decay. So next thing, unless you got anybody got questions on that. Radon 222 is a decay product of 238 with a half life of 4.5 billion years. Radon is a gas. Okay, it can diffuse through
Yes.
rocks and microfissions. Okay, and cleft plates where it's been sliced.
It
Um,
can accumulate in your basement.
Radon is, I believe, heavier than air, is it not?
Yes, it is.
Yeah, because you have radon detectors, also carbon monoxide. Radon, they actually have radon detectors because radon will actually,
If you have a super insulated house
yeah,
and you've got things like concrete that has radioactive materials in it, the radon will seep out and will sit
yeah. Of
down
course, it's
and
heavier than air. It's 222. Obviously, there's not much
yeah.
in air. Yeah, so that's kind of stupid of me to say. But yeah, when I'm trying, I was trying to think of how much escapes. It will, if you have poor ventilation, accumulate in your basement. There you go. So it has a half life of 3 days, which is millions of times longer than some other isotopes of radon. So most radon is very, very quick, microseconds. But radon 222, if I'm not mistaken, is the longest half life of radon. So the fact that it exists at 3 days
Yeah.
is plenty of time to migrate.
And if we go back to here, if you look at radon here, this is the you know this is the 3.8 days is the long half life one that's in
Yeah,
here.
if it was any other radon, then we wouldn't see these polonium halos. It'd be hard to explain them because if you decay in microseconds, then we would expect that decay to happen in the concentric halos of the parent isotopes.
Yeah.
Um, so what happens is that these polonium compounds will precipitate to more favorable sites in the rocks. In other words, they just diffuse. Or more likely, what happens is you have water through rain or something else, and that water will seep through these microfissions. And
Yeah.
then you'll end up with uranium over here, and you end up with polonium that's supposed to be here. Actually, because of uranium, radon, the radon gas will dissolve in the water, go through the water, and end up in a microfissure somewhere else.
Yeah.
Not that far. As a matter of fact, Gentry never saw, that I recall, a polonium halo without some uranium around it. Okay, so it was never too far from a uranium thing, and there's microfissures. So what he was seeing was the fact that this polonium was not created in situ ex nihilo. It was transported there through water or gaseous diffusion from the decay chain of the uranium.
Yeah. And again, radon is a inert gas. It's in the it's in the periodic column. Things like helium, neon, argon, and friends. And it's not going to be chemically reactive with things, and it's able to diffuse through stuff easier than if it was something like nitrogen that will bond and form bonds with their materials.
Absolutely. And so this was a much more likely scenario, much more likely conclusion of why we see the observations we do. Long story short, Gentry eventually had to concede that in order to get his theory to work or hypothesis to work, he had to once again invoke singularities. One time off, and I mean differently than what you think of. His what he calls singularities were one time off things where God intervened. God made it look the way it looked because reasons, which again, as we all know, is last Thursdayism or the Omphalos hypothesis. Science doesn't work that way. You can't say in a paper because he was trying to do legit science. Okay, he's a legit physicist, but he's also a young creationist. But when the science went against him, he had no choice but to say, well, at this point, we're invoking a miracle. We're invoking
Yeah.
supernatural causation. He's no longer in the realm of science. He was debunked at that point. You don't hear much from Gentry any longer. He's still out
Right.
somewhere in the creationist circles, but you don't hear as much when I was growing up. This was a big thing. Polonium halos. I didn't have the education back then to understand it, but it was a big thing. But you don't hear this argument very much, except for people that are unfamiliar with it and that don't know the science and they think it's a good argument. But if you
Yeah.
ever find those people, send them this video. And I also have this PowerPoint presentation that I've done on my channel in total, and you can send it and they can watch that.
Yeah.
So,
So somebody asked here, so where does biology move these elements through the isotopes through this chain? Um,
what's that?
so they say, so where does biology move these elements through the isotopes through this chain? We're talking about the decay chain.
What do you mean by biology?
And that's what I say. I don't. This is not a biology thing. This is a
Yeah, you have
level.
let's say you have an atom that's uranium 235. We'll call that the, like I said, the nucleation point. It's right here.
Mhm.
Okay, that's going to decay. Poof, and it has an alpha particle that's going to go out. That's going to cause a track. That's going to be part of that halo.
Yeah. So you got 238, which is the most common uranium. It's going to alpha decay to thorium
That's going to
at,
thorium.
at a certain energy level, right?
Yep, thorium's going to beta decay to uranium 234. Then uranium 234 is going to produce an alpha particle. That alpha particle is going to go up, and that's going to produce part of another halo at a different energy
Mm-hmm.
level because your energy
Yeah.
level for these photons. That's all. That's all these. It's not a photon. I'm sorry. Alpha particle. Photon's a gamma particle, but
Yeah.
photon. These alpha particles is going to have a different energy level for uranium as it is 234 from 238. They're going to be different. That's why they produce different halos because the penetrating power is different. The ionization potential is different. The energy levels are different.
Yeah. And so every time you see an alpha particle in here, it's going to have a different energy level. It's going to have a different radius from the site. But also remember that these materials can move, and so particularly like radon gas, which is chemically inert, can much more easily move through a lattice than something like your uranium, which is chemical properties that will bind.
Yeah, the other ones don't move that much, right? I mean they're going to stay pretty much where they've decayed into. They're going to stay in situ there, but the gas, it's a big difference. The big gas can actually diffuse. A solid won't. Well, you can have solid diffusion, but in this particular case, you're not going to have solid diffusion. You're going to have gaseous diffusion, and you're also going to have gaseous diffusion um, in some kind of solute. And the solute, that's going to be what's going through these microfissions. And what I mean
Yeah.
by solute just means it's in a solution. Which, by the way, anybody out there, aqueous solution always means water because aqueous solution means water. So if you hear any idiot out there in the internet say, "Well, most aqueous solutions are water," that person's an idiot. And there's only one person I've ever heard say that. And guess what? That person's an idiot. We all know
Yeah.
who that is. I'm not going to mention them, but
Yeah.
you can go look that up because it's hilarious. Have you ever heard that before? Somebody actually saying, "Well, most aqueous solutions are made out of water." Well, no, like all of them are. Um, God,
Otherwise, they wouldn't be aqueous.
oh God.
Yeah.
Gender's
So
collision.
like that basically saying most water solutions are made with water.
Yeah, the only way that would logically make sense, and this is going to be off topic, but most in logic, modal, and if you do modal logic, most would be included in all, right? Because if you say some of p, that is included of all of p, so that would work, I think. But I don't think that's the way he was using it. But
Yeah.
anyways, Gentry's conclusions were faulty upon this because one, he had an unsupported assumption of that 1/2000 factor to relate how much the penetration power would be in free space or air as opposed to granite or biotite. Um, he also failed to provide any accounting for his claim that those samples were primordial polonium. He said they were formed from primordial granite from the formation of the Earth. Now, this is billions of years after that. I think these rocks were only a couple hundred millions of years old, not
Sure.
billions. Some of them were. I mean, obviously, you have uranium that has a half life of 4 billion years, but that has been around for that some long. But the rocks that he was using, a lot of that rock was much younger than rock, but it had uranium in it. Those were just part of it. Anyways, failure to provide an accurate measurement of the halos due to instrument error and the ion probe's resolving power. Remember, he only had a 2 micron ability to see things. Imagine having a microscope. An ion probe basically vaporizes stuff. It makes a plasma, and then it takes it through a chromatic spectrograph, and basically tells you what. Wait, okay, wait a minute. I've seen ion probes, but there's an ion probe that. How does it actually work? I'm trying to remember how an ion probe works. So the way I remember an ion probe is it actually would vaporize material and you run through a chromatograph. But I don't remember how an ion probe works to see what he was seeing on this. Do you
Well,
remember?
isn't ion probe having a tip with an ion on the bottom of it, and you're looking at the force of the
Is that what it
ion
is?
probe?
So okay, that makes sense. Okay, that makes sense. Yeah, I remember. So you have basically you just have an ion here, and that's having a potential to whatever you're looking at, and they're taking a difference of that force, and that force is causing an image,
Yeah, I
right?
mean, or you basically measure the forces as you move across
Okay,
something.
a long time. I don't remember that, so I'm gonna leave that to them to go look up
And,
because
and
I don't
so
remember.
and so and so the ion can move up and down. You can get a change of current. You can measure the current on a tip. If you're talking about,
But how's that gonna resolve to an image?
I mean, you're talking about like scanning tunnel. Is
Well,
that what
that's
you're
how I would
referring
think
to?
for a scanning tunnel microscope, or scanning electron
Yes.
tunnel microscope. But I don't remember the probe he used for this. I just remember the resolution factor.
So
So
I
forgive
thought you
me.
were referring to a scanning tunnel because that's how
It could be. Maybe he was using. I don't remember what ion probe he used for this. I remember all I remember when I did this research was that the resolution for the ion probe was less than the resolution for the discrimination of the rings.
yeah.
He also again he eliminated beta particles. Not a big deal now. We do know now that they are alpha particles, but there is damage because of a beta. That damage because of beta can actually, unfortunately, again blur the lines of the crisp lines we would expect. It would be kind of blurred. So you blur radon 222 with polonium, and you can't really tell what caused it. So when we see a polonium halo over here, it's probably more likely in a radion halo, a 222 radion halo, but it's so close together with each other because of the energy levels and the lack of resolution. He just thought it was a polonium halo. So
Yeah.
he's calling them polonium halos, but they're probably polonium halos in a radion halo that came from through seepage or fission, diffusion, through the microfissions from the uranium halos.
Yeah.
Yeah.
So in other words, again, if you go back to this decay chain, um, you have the ability for this radon to propagate through the material and move to a different site, so that when you see the halo from polonium 218, that alpha particle can come from what looks like a brand new spot, as opposed to it was uranium and it migrated, and then the radon decayed.
Yeah, well, actually, I mean, it really is a new nucleation point because you now have the uranium decaying. Now you have gaseous radon. The gaseous radon moves over a little bit, a couple centimeters. Now you have a new nucleation point, and so all the decay products will be from that new nucleation point. But since the energy levels are very similar, it's indistinguishable from the radon. So Gentry didn't take that into account.
Yeah.
Yeah, but anyways, I think that's about it. So what's the next slide? Yep.
End of presentation.
So let me clear this out real quick. Go back in screen. Um, let me,
So again, the takeaway from folks is that this was an attempt by somebody to say, look, we see these little spots, these halos, which they claim only come from polonium. And since this polonium has a very short half-life, therefore the Earth was effectively his argument. So people said, no, these particular spots can come from radon migration. There you can also see radon halos. Your resolving power doesn't let you distinguish between other decay products. So no.
yeah, I mean, and again, what is more likely? I mean, when we're talking about science here, we have now a scientific explanation. This goes back to the 70s. All the research papers that I looked at to come to my presentation, also a lot from Talk Origin, which, by the way, very difficult read. Talk Origin does not make it simple. I actually had to look at multiple sources to actually distill this down to make a PowerPoint when I did this, and this was about a year or two ago. So forgive me, I'm not. I'm a little rusty on this, but the Talk Origin is not easy read. But what's more likely, what we've described using natural mechanisms, or that the Earth was formed in a matter of 3 minutes and is only 7,000 years old. Right? And yes, this actually is my desktop. It actually, all this stuff moves around. Is that kind of cool? This is actually a working calendar. My clock moves. Yeah. All this stuff moves.
Actually, right now we only see your background.
Well, you can't see it. The outside can
Oh,
see it
oh, sorry,
because I
sorry,
have it.
sorry.
I have it in the middle window. But yeah, all this stuff is configurable. I just thought it looked cool, so I did it this way. But okay, so last minute questions because we're going at 90 minutes and it's very hot. I'm very tired. It's been a long day. Landon had something with Milwaukee Atheist. By the way, I saw them earlier. Hey, Milwaukee Atheist.
Oh,
Um,
hello.
they followed you over here.
They're nice folks. You can go and subscribe to them as well.
Oh, I have.
Um, so again, this is one of those attempts to try to say, "Oh, I can prove the Earth is young." It's like, no, that's the one sentence summary of the talk.
That's basically it in a nutshell. So, guys, I want to thank everybody for watching this. Yeah, this was again very quick and dirty. I had no time to prepare for this whatsoever. I didn't even look at any of these hardly slides until 5 minutes before we went on air, basically, because I haven't done this in a very long time. This is a 2 year old presentation. So if I was too fast or if I didn't explain things properly, that's all on me. Please forgive me. But I think you got the gist of the idea. So if you kind of
So,
like
any
go
questions,
through
any
it,
comments from the chat?
not that I can see. Let's
So
see
it was
here.
51. So it was one time it was 51 people watching. So I'm not sure how to spell it, but it's how it sounds. Okay. Looking at things. C. Um, and I think again, and you talk about, there's been um, when someone talks about dating, right? Let me ask this: if someone says, "Okay, we've radioactively dated this rock to be, this many billion years old," um, how do they do that?
Well, there's two different ways. I mean, there's absolute dating and there's relative dating, right? And relative dating is basically saying, okay, here's this rock, and we're gonna make a relative dating between them. But absolute dating is using isochron dating methods or some kind of radioactive dating method. And the way that basically works is kind of simple. They basically say we know the half-life of this material. We know how much material we have. Know how much daughter materials we have. We can calculate the age of something by saying, okay, well, how long did it take to get from that to this? Well, it took a billion years. Well, this rock has to be a billion years old then. Um, and what it would produce is this nice clean line called a isochron line. And that only works for certain materials, isochron dating methods, but it's not the same thing as what we described. What we described was more like carbon dating. Carbon dating would be using the methods I described, but isochron uses geochromatic type formulas. They're very complicated formulas that I don't even remotely understand. But it's based upon even uses Taylor series, but not. These formulas based upon
Yeah.
Taylor series. So they're very high level calculus. But by looking at that line and see if it's straight, they know they've got a correct proportion of daughter to parent isotopes, and they know the age of the thing. And they have no contamination because contamination will make that line
Yeah. So you might have a
skewed.
crystal that contains radioactive material, and you look at and you go and you pull the crystal out, crystal's still intact, and if you dissolve the crystal and you look at the amount of this isotope versus that isotope, and for example, if you saw a crystal that was formed, trapped this radioactive material, and it went for one half life, right? You would expect essentially that you go from zero old to new to half as an example, or
Yeah,
half as it's decayed. If you saw something else that said, well, it's a quarter and three quarters, right? It meant you've gone through two half lives. So that would say that this crystal has stayed intact for two half lives, or whatever this radioactive material is.
yep. And the more
You
half lives it
pick,
stayed intact, the older it is.
yeah. So what you're doing is you're saying, all right. So if you had something that's a billion year half life, and you saw a crystal that essentially three quarters of the material had decayed, you say, well, it's gone through 1 billion year half lives. It's 2 billion years older than this other material that doesn't have it, right? So and there's many different types of decay products. So you pick your decay product that is going to have a time frame, because you're not going to use something that you're not going to use like uranium at 4.5 billion years to try to date something that came from the 1600s, right? That's not enough time, right?
Wrong
You
tool for
need
the
a
job.
yeah, you need a decay mode that's within the range of the kind of ages you're looking for.
And it should be noted that one of the unresolved issues out there with the RAPE project, which was the project that younger creationists were trying to show that evidence that the age of the Earth is young, there's a couple unresolved issues, and one of the major ones is the heat problem. And the heat problem is pretty simple. All it is saying that is how is it that we have this amount of energy that we would expect to see in this system that we know it from radiometric decay over millions of years. We need to account for all that energy in a period of 6,000 years. Okay? Because it produces a lot of heat. In fact, most of the energy in the Earth is produced from radiometric decay. A lot of it is
I mean,
from decay, from thorium.
why do we still have magma and lava coming on the surface? Is because the heat it literally is being heated by deep in the earth, radioactive materials decay, and it's the warmth of the radioactive decay. Why is there warmth? Remember those alpha particles, beta particles? They're zipping through rocks, banging on things,
That
knocking
produces
these
kinetic
around,
energy. That's heat.
and that's heat,
Yep.
right? It's so if you're going to take all of this radioactive material and rapidly decay it, well, you're going to produce an enormous amount of heat, and you're going to be vaporizing rock
Yeah.
and
Technically heat is the movement of thermal energy from a concentration region of higher concentration to lower concentration. But kinetic energy obviously imparts energy. That's going to cause a differential. So if you have a higher kinetic energy state and a lower kinetic energy state, the higher kinetic energy state is obviously going to be at a higher temperature. Heat is going to be the energy flow from that higher concentration to lower concentration.
yeah. So
But
someone says
by the way,
if
I just real quick. They can't. The long story short, they can't account for that. They still can't. They posit this thing called accelerated decay, but they never demonstrated that accelerated decay exists or even possible. Well,
because
I guess anything's possible, but
they put it say, well, how do you account for this thing and say, well, sometime in the past, stuff was decaying faster. Well, okay, if stuff is decaying faster, that means it was producing that much more
right.
heat. And where is all that heat, right? If it's hot enough under the standard Earth model to cause volcanic eruptions, if you compress that down to a few years, you'd have bits of the Earth vaporizing from all the energy.
The amount of energy would be enough to liquefy the mantle. So, and by the way,
Yeah,
when I say the word possible, I would should say it's possible metaphysically, but against the laws of physics. The laws of
yeah,
physics don't allow for accelerated decay. There's a lot of
yeah.
reasons why it'll screw
Okay.
up your speed of light constant. It'll screw up your fine structure constant. It'll screw up your electromagnetic permittivity and permissivity. All these really cool fundamental constants that hold the atom together wouldn't work. It would
Yeah.
be very very
So,
bad.
so someone says if all heavier elements are created through acceleration of fusion events in supernova, and what's inside Earth must have been present in the solar system for at least to the time the Earth's formed. Do we know of uranium deposits with different half-lives?
Well,
Like one supernova happened 4.8 billion years ago.
our sun is a fourth generation star. There's been three, if I remember correctly. There's been
Three,
three.
third.
Is it third or fourth? I thought there was three prior, but it could be a third generation.
I thought it was third
All right. Well, you're the
population.
astronomer, so I'm going to go with you. But it is.
Yeah.
It's not the first one. Okay. Let's assume. Let's go third generation. So there's been two other generations of stars prior to ours. But uranium is uranium. It doesn't matter what produced it. It's still going to have the same decay constant. It's still going to be 4.5 billion years, 4.58 billion years. It's still going to be
Yeah.
no matter what produced it. That doesn't matter. It's a fundamental
Now,
constant of that nucleon. Assuming that nucleus configuration. And why nucleuses are the way they are and how far they can go, like to element 118, is really cool. And really, if you look about to go research something interesting, go look into why elements are the way they are and why the limitation is what it is. And it's amazing. I mean, they can't. I think the highest theoretical is 127, if I'm not mistaken, but it could be 137. I don't remember. Element 137 is it? I haven't.
Well, there's a one that Feynman said essentially
Feynman,
that
yeah.
if you had a nucleus like this, the electrons would have to exceed the speed of light in
And that's
order.
what it is, right? It's based upon relativistic effects, right, Landon? Exactly. See, Landon's genius. He knows. He's like, this is like super easy for him because he's literally a genius in all this shit. For me, I actually had to go study this crap, right, back in nuke school and other things.
Well,
But
I
yes,
cheated because I had a conversation with Feynman.
yeah, he knows. He knew Feynman. The guy actually talked to Feynman. But Feynman's thing on this, correct me if I'm wrong, because I'm just an idiot on this stuff compared to you. Feynman's argument was basically you have relativistic effects in that the electrons in the Bohr model, but still it still has some kind of ontological thing, would have to be traveling at the speed of faster than the speed of light on the s orbitals to have an atom with greater than like 127 or 137 something protons. Would that be something along those lines? There are
Yeah,
relativistic effects on the
and
electrons.
but then as we started discussing, because I was asking about how far can nuclear synthesis go, and he said, well, there's this thing. I said, well, where is it? So you can calculate it this way, but of course there's other things that come into other details come into effect because the structure of how the nucleons are packed in a nucleus is changes as you get higher atomic
Well, the
weights.
orbital
Not quite.
configurations, yeah, because you obviously have changes in your s orbital, p orbital, f, d, f. Then I think it's like G. Then it has like H. I mean, it has all these different orbitals that I never really bothered to memorize because you don't.
So one of the questions could you could potentially have nuclei, but they were always in an ionized state. That is what you could really say is, okay, there might be a limit to how big a neutral atom could be because the
Yes.
electrons outside would not work well. But also the other question is whether or not those orbitals start to collapse as you get larger and larger. If they start to get
Well, yeah, they're not stable any longer because again, you're having a more mass in the center, which by the way is way far, relatively speaking, from the orbitals. But more importantly, what's holding that together is still the residual effect or the secondary effect from the strong nuclear force that's inside the nucleons itself. So you have inside the neutron, inside the protons, you have a quark structure. So you have what's two up and one down, or one down, two up. And those quarks are being held together by gluons. And that whole thing is what's called the strong nuclear force. But there happens to be a secondary effect of that. And that secondary effect carries across the boundary of the nucleon, and that's actually what holds the nucleus together and is enough to overcome the repulsive force from electrostatics of the protons having the same charge. You would think, has anybody ever thought, why does an atom hold together? You've got these neutrons, you've got these protons. Wait, protons are the same charge.
charge, why don't they just go boing,
Poof,
right?
right? But there's a reason why they don't go poof, because the strong nuclear force from the actual bonds inside the neutrons and protons is what's holding that together. Pretty cool, huh?
Yeah, and so there's a strong nuclear force keeps them together, and it's a short acting force.
Very short.
But that's basically surrounds the nucleus and keeps it together. But decay is one of the cases where you get modes inside the bonds. Basically, you get these oscillations inside there that will end up causing a a four nucleon, two protons, two neutrons, to sort of get isolated on one side, far enough away from the parent nucleus where the strong nuclear force can no longer hold it in, and now it feels the repulsive force of the positive charges of the nucleus and it is positive charges, and that's what kicks it away. The energy, when it said, "Oh, this thing goes up at 4.5 million electron volts," that comes from when that alpha particle gets isolated. How long it takes it to get isolated, and then that will give you the repulsion. So something that gets isolated very close to the nuclei will have a really an enormous repulsive force, and will go out much faster than something that forms farther out.
I think you need to stop because you're getting Raising Girl excited.
Okay.
She just loves listening to your voice.
Sorry.
No, that's a good thing.
So
No, Raisin's awesome. So
so back to the thing about talking about
we don't want to get her too worked up though.
the supernova. So when these stars, when particularly like type 2 supernovae, let's say a star collapses and you get this enormous enormous explosion. Some of some of the most enormous explosions we see in the universe occur, that's where the really heavy elements get, some of the really heavy elements get created. There's other things that neutron star collisions can also do the stuff. And so when how the star collapses and how fast it collapses has somewhat an effect on the mix of atoms that fly out of it. Because normally what a star is going to do is that your J star is going to take hydrogen, fuse it to helium, and that's about, you know, but then it goes through cycles where it will fuse to, you'll get heavier and heavier elements up to the point where if it's big enough, massive enough, you'll get fusing of iron. And when fusing iron, that absorbs energy rather than gives off energy, and the star collapses. And it, literally the sound waves crush the material. The star, the outside of level layers of the star that's falling in. Because let's step back. Why is the sun as big as it is? Well, it's the balance point between the nuclear explosion, the fusion inside that wants to blow it apart, and gravity wants to keep it together.
Well, it's gamma pressure. Be
Right?
specific. There's a balance between the gravity, the weight of the star, and gamma pressure, which are the gamma photons coming out from those nuclear reactions specifically. So
Yeah.
that gamma pressure is balanced with the gravity. So what happens is if you start losing fusions, right? Because it's called the May-West curve, which is outdated. It's sexist now. I learned of the May-West curve. Screw off. That's what it's called. But it's actually called the fission yield curve as well.
Yeah.
But the
Yeah.
May-West curve is basically, it looks like this, right? It looks like boobs. That's why they call it May-West. She had big boobs.
Yeah.
Um, but if you look on the curve, it basically says what atom is going to give you energy if you split apart, what atom is going to give you energy if you put energy into the system. Fusion is you put energy in, right? That's where you need high temperatures. Then it'll fuse and you get more energy out. But iron, like iron 56, doesn't do that. You would actually have to put more energy in to the system than you get out. And so once a star reaches a certain level, it'll go through hydrogen to helium, it'll go through helium to lithium, and then beryllium, and it has carbon, nitrogen, oxygen cycle that it goes through, and then it starts producing iron,
Silicon,
silicon, nickel, all these
yeah,
different elements, right?
and then
So,
you get to iron.
and then you get to iron, and the star says, "What am I going to do with this iron?" And it starts losing that war, that tug of war between the gravity and the gamma
It wants to
pressure.
crush it, right?
So
And
it
so
starts crushing it.
so it
Right.
falls in, and literally by the time once it starts fusing iron, it literally it's a matter of minutes where the outer layers fall in, and they reach a like about a quarter of the speed of light as they're falling inwards towards the core. The thing slams together, and if you get enough oomph, that momentum is going to actually overcome the atomic forces, and the nuclei will crash together, and you'll get this shock wave, literally a sound wave that'll crush through the star.
But what causes it to
Crushing
bounces back out? That sound wave, like you said, it crushes back in, but all of a sudden, then it bounces. It has a reflection, and that's what causes the star to explode.
There's several models on the mode. One of them certainly is the shock wave rebounds, right?
The shock wave rebound,
it
right?
bounces off and comes back on. A second is an amazing effect of neutrino pressure, because when you're fusing these things, you're generating neutrinos.
Would it be a case of neutron degenerative pressure?
That's one thing that's going to stop you, right?
So you have okay. So the couple things that can happen then, and I know we're getting off topic, but you guys are interested in this, and I love this kind of stuff too. So it could when the star goes into that supernova, you could be held up by electron degenerative pressures, right? So basically, the electrons are so close together, they're having a repulsive force, but that's pretty compact. That's what we call a white dwarf, right?
Mm-hmm.
Then if it gets compressed any further, then you actually go into the neutron degenerative pressure. So basically, all the protons, or most of them, are combined with the electrons. Basically, the electrons are shoved into the protons. Proton plus electron, blah, 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 produces a neutron. So that star now becomes held up by neutron degenerative pressures, and it becomes basically, as far as wave function, one big neutron.
Yeah, it's just one giant atom in there,
Yeah.
and the shock wave goes through that and back the other side. And the other thing is that you also generate neutrinos, right? All those protons get you kick off electrons and neutrinos, and while neutrinos don't interact with matter very much, they do interact to some extent, but you get such high densities,
Unbelievable
in there
densities.
that the neutrinos actually start to push against the material. So because a certain percentage, a non-trivial percentage, like around 10 to 15% of the mass gets turned into neutrinos, and there's so many neutrinos pushing on it that there's another force that's essentially going to blow off the outer layers. It is just extraordinarily
Well,
amazing how much energy comes out of this supernova.
I got a surprise for you, Landon.
Yes.
I have next week coming in, and hopefully you can join us. But I know that you want to do this kind of every other week. I didn't do this last week because of the holiday, but we might be doing DEF CON every other week. I don't know. I haven't decided yet. But I actually have Dr. Kroon coming in. He's an astrophysicist.
Oh, okay.
He has changed his job, or will be changing his job in the next couple of days. And as soon as
That's
he's
fine.
out from contractual obligations in this new job, he'll have free time. And he's been dying to get on here. An
Excellent.
astrophysicist has been dying to get on here,
Um,
and he wants to talk about a lot of this stuff. He wants to talk about all that kind of. He wants to talk about cosmic event horizons. He wants to talk about black holes. He just loves what we're doing. Loves the non sequitur show, and I've been corresponding with him for a while. But he's just unfortunately he works for a very secret thing, and they said you can't do this. You can't do this while you're on contract. But his contract expires in 2 days, so then he can. So
yeah.
3 days. So
So
that's
I
gonna come
think
next week. So if we want to deal with that, we could come up with a game plan and let's talk cosmology, man.
I should let's just conclude back to saying the original question. One of the reasons why we say the model is that there were two supernovae, one 4.8 billion years ago, one from 4.7 billion years ago, is that we can see the bimodal decay, that the 4.8 billion year supernovae sent out a bunch of heavy material, some of which got stuck into the nebula which our sun was forming in, and those began to decay. And 100 million years later, another supernovae nearby also went off, and its material stuck in. So we got basically two hits or two seeds of radioactive material that came into our set. So the start of the decay comes from the release from the supernovae, and we see that bimodal thing with the two peaks being 100 million years apart. And so that's where the model, and we know the rate of decay, so we can work backwards and say 4.8 billion years ago, 4.7 billion years ago, two supernovae. And then the assumption is that the first supernovae, 4.8 billion years ago, hit the gas cloud that was relatively diffuse. There might have, and there was a knot in there, the nodule of protostar that became our sun. So it had a little bit higher density. So the material that came into the nebula got stuck into it's like dust coming in, got stuck in this cloud. It also compressed it a bit, so it became more dense. That slightly more dense material had gravitational forces started to pack things in higher and tighter. So when the second wave came along 100 million years later, it's seeded with even more material. So most of the heavy material that are around Earth, right, that are in you, like the calcium in your bones, the iron in the steel frames of your car, all that sort of stuff, most of it came from the second supernovae. Why? Because the first supernovae had to kind of collapse the gas cloud a little bit, and now you had a dense nodule that allowed the second blast to really stick into it quite well. But the two radioactive decay products are offset by 100 million years. We can see that in the record. Now, by that meaning that the solar system began to slightly form at the 4.8 billion year range, and it started collapsing under the weight of the protostar. Massive protostar started collapsing, got seeded 100 million years later at 4.7 billion years ago. And it wasn't until our star switched on around 4.6 billion years ago, and the gas clouds that were forming around it accreted into lumps, one of which became the Earth around 4.5, 4.6 billion years ago.
Yep, and the rest came the other planets.
Yep.
So I think I would wrap this up a little bit. I can ask the people in the live chat if they got any other questions. If not, leave a comment on the video of what you would like to see. I've got another presentation that I did a long time ago that I'm thinking about doing, but I need a biologist with me. But I did a presentation on central dogma biology, basically DNA to messenger RNA to protein, how that actually works, which actually works out well. The fact that we just had John Perry from Stated Clearly on recently kind of touched on it, and we had Dr. Nathaniel Jameson on talking about biology. So a lot of people have actually, said, I don't understand this whole DNA thing. I don't understand how proteins relate to DNA. I don't understand when they're talking about RNA. And I just happened to do a presentation on it a long time ago, a very basic PowerPoint presentation. But I would like to have a biologist involved. So maybe if Landon and I can find a biologist, we can do that
Yeah,
coming up
sure.
as well. Because Landon and I, we have basic biology. We do have the basic understanding, but I want to have always an expert on this show, if
Yeah,
possible. Like we had Dr. Rachel Traylor on, a mathematician, and granted, Landon clearly is an expert in everything, but he's a host. I want to have guests on that are experts,
yeah,
to kind of back us up and stuff like that. Plus, they're the experts. I mean, if we have somebody in biology, either one of us, we're just
yeah.
lay
And
people
even
in
like mathematics,
biology.
Dr. Trailer has different expertise in mathematics than I do. Similar thing, I imagine with this cause, this astrophysics coming on, we have, I'm a planetary scientist. He might be more of a cosmologist, but
He's
but
got,
again,
more cosmo. Yeah,
questions that someone asked in terms of why do some stars become supernovae while some become black holes? Well, there are stellar mass black holes are one of them. One of their methods of forming is from a type 2 supernova star collapse. So there are the massive stars that run out of nuclear fuel that collapse form a supernovae, but not all supernovae form black holes. You have to have enough material to crush, right? If you don't have enough material to crush, and usually it's, I think the number is around
three.
nine.
What's three solar mass? 3 kilometers. You have to have enough. You have enough. If you compress the entire sun into 2.95 kilometers, so just under 3 kilometers, that's going to be within under the Schwarzschild radius. That'll be enough to cause a black hole.
So if you have a star that's around 9 times the mass of our sun and it collapses, you're pretty likely to be able to form a black hole. You have stuff that's only 2 to 3 times the mass of our sun. You're not going to form a black hole, right?
Right.
It won't. And in fact, below the 1.4 Chandrasekhar limit, it won't even supernovae collapse. It'll just form a white dwarf and sit there and smolder. So so the answer is it's based upon the mass of the original star. And the other second thing is how it collapses. Someone else was asking,
And
what
wait,
are you drinking?
there's another limit too, but I forget the name of it. I always do. There's three names involved with it. But is it Shandeskar? Is that how you pronounce it? Shandeskar?
Chandrasekhar.
Yeah, Chandrasekhar. The Chandrasekhar limit would be for electron degenerative pressure. So Chandrasekhar would be for how much the limit would be to produce a white dwarf, right? So you have the Schwarzschild radius would be the limit for which a enough solar mass is in a small area, 3 kilometers, to form a black hole. But the
Chandrasekhar.
Chandrasekhar limit is for electron degenerate pressures and white dwarfs, and there's another one for neutron stars, but it's three
Yeah.
names. It starts with a T, and I can never remember it.
Oh, I'm trying
And
to
I'm
remember
not
too.
looking anything up. I haven't Googled shit, so everything I do is pretty much off the top of my head. I don't even have a laptop here or anything. So,
I'm trying to remember that
but
name.
it's something 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 limit, and it starts with a T. I
Yeah.
used to know it, but I
And
don't study this stuff any longer. I don't even bother with it. I just
yeah.
happen to have a vague recollection.
Someone was asking what we're drinking tonight. I was having Lion Ranch Viognier dessert wine, which was a sort of a celebration of having made it through the Milwaukee Atheists event. But I think I'm going to switch over to a nice red wine. And so that question that's been asked several times about what am I going to drink next is going to be I have to switch back to a red wine. And so, but there's an app for this where I have my cellar and I say red and then say, well, what might I have? And so one possibility is a Costa Brown Pinot Noir 2015. There's a Russian River Valley
I like Pinot Noir.
has a really, and Costa Brown, KOSTABROWNE.
I have some Chardonnay left, and I think I might dive into that tonight. But
Yeah.
yeah, you're just a cork sniffer.
Absolutely, I'm quite a proud course lever. Although I actually, ironically, the one I had for the Milk of the Atheist doesn't even have a cork. It was a screw top.
Oh, heathen,
Screw
heathen,
corks.
heathen. Screw corks.
Screw. I don't mean that in that sense. I mean the screw
Yeah, I
cork.
know what you mean by it, but yeah, yeah.
You know the one where you screw
Tolman
it
Op.
in that way.
Yeah. By the way, somebody had mentioned. Thank you for. Yeah, it's the Tolman Oppenheimer Volkov limit. Thank you.
Ah,
But you can
thank you. You're
understand
right.
why
You're
I
right.
don't.
You're right.
But now you get why I
Ah,
just
that's
don't
right.
do a lot of this
Oh,
shit because
thank you. Yes, it is.
I know
It's
if, like, for example, if he would have say Tolman Oppenheimer Volkov limit, I know exactly what the frick he's talking about, right? But
yeah,
don't
you're right.
expect me to
I
remember these things
remember.
because I don't ever I don't bring up the Tolman Oppenheimer Volkov limit. I just happen to know there's a limit starts with a T that has three
I remember
names.
it because I knew I should
That
have known
that's
them because
yeah. I don't.
studied
I'm not an astrophysicist.
studied
What
a
do you
lot of
want?
stuff about Oppenheimer's work
Yeah.
that he did. But back to the thing about the stuff.
Hey, I'm
I think
surprised. I gotta admit though, it's pretty impressive. I at least remember it starts with a T and has three names, right? And what it
yes.
relates to. That's more than most people. So
And I say for quarks, I'm not talking about quarks as in inside nuclei, but quarks as in the bark of the tree that's commonly grown in places like
yeah,
Portugal. The quarks, while being traditional, also are a really good way to get wine to spoil. They unevenly age the wine, and they can decay and break apart in the bottle and so forth. A compromise that uses synthetic cork. I prefer a screw cap, right, where the bottle is sealed and there's a cap on the top of it, and the wine stays in there and the air stays doesn't mix, and you get a much more consistent wine product.
sounds good. I'm a big fan of wine, but I like the sweeter wines. Some dry wines. I'll drink like a Chardonnay with fish. But anyways, we do got to wrap this up. It's going well beyond 2.5 hours. Uh, So,
Yeah.
anyways, live feed. Thank you for watching this. I know this is kind of a niche thing. I know we don't get a big as audience as I do when I do my hangouts or rum and coke nights or non sequitur show. I get that. This is strictly, basically, going to be Landon and I, and maybe a few other people that come on. We're going to be just talking about science. And I think as we go, I want to get more in depth. And I think this presentation did involve a lot of mathematical concepts that people may have not been exposed to. But that's what I want this direction to this kind of show to show that a lot of stuff isn't as scary as people make it out to be. But I want it to be that people can digest this stuff because look at it is understandable. I may not remember how to do a lot of this stuff, but I do remember some of the concepts. And if I can relate it to you, then you can understand it because I don't deal with this stuff any longer. So that's the kind of the whole goal. Just
And when
relate.
we use math, we'll talk about what does the math telling you? We'll say, and therefore what? We won't just leave you a bunch of equations, right? It'll be there.
It'll
And
make
so
sense.
the decay mode says the rate of decay will tell you about the decay constant. Well, the energy will tell you how far the thing moves out before it gets stopped. That'll produce a defect in the crystal lattice, which you can observe. This guy didn't understand, didn't have a good enough resolving power, didn't count for decay products migrating, and so his young Earth creation stuff was debunked.
That's in a nutshell, and I hope everybody got that takeaway. I mean, I hope everybody that watches this video and go watches the original if you find it. It's just radio. It's called radioactive radio um, radiometric. I don't remember. Polonium halos debunked or something. That's what I don't
Yeah.
remember what I named it. But just look for polonium halos debunked, and you'll find it. Same presentation, only I went through a lot more slower and a lot more fresh in my mind because again, I haven't looked at this stuff in a very long time. So I appreciate
So
the fact people do watch this, and I appreciate the fact that people want to learn this stuff, and the fact that again, it's been so long, and yet I hope it made sense.
I mean,
You know.
and as I said, there were 49 people watching. So thank you very much. And hit that thumbs up button there if you happen to like it, or a thumbs down if you don't like it. And as I say, maybe in 2 weeks again, this gentleman named this astrophysicist that wants to
Dr.
join
Bennett,
us.
yeah, yeah, he'll probably come on. I think next week that he wants to come on. Um, we'll figure out a subject, but he's You can talk about a lot of different things. I wanted to talk about Big Bang cosmology. I wanted to talk about the Big Bounce, the Big Crunch, horizon problem, problems with the maybe with the anisotropies in the cosmic microwave background radiation that is used for geocentrism, that kind of stuff. I'd be fascinated, and just show some of the math. I mean, even stuff like these the redshift of quantum of the galaxies. Remember that young creationists were talking about quantized redshifts.
Yeah.
That would be
But I
something
mean,
interesting to
and
talk about.
trying to talk about, when we say, oh, something is 5 billion light years away, and people say, well, what is it like now? Well, what they're really saying when they say something is 5 billion light years away is that when light left, it took 5 billion years to reach here, and that we say 5 billion light years away because at the time the universe was that big to allow
It's a
the
lot
universe
further away now.
was a size such that at the time it left, the universe was small enough that it only took 5 billion years to get here.
So if you guys got ideas for the shows, please let us know in the comments. But with that, Ryan, you got anything else? You want to promote anything and
I would,
call it a day?
as I say, I would encourage people to continue to ask questions, continue to join their favorite universe. Certainly subscribe to this channel, and also become a patron of
I appreciate that.
Great Society. They're good folk, and they do a lot of hard work. These folks work an enormous amount behind the scenes to do that. And while you're spreading around a few subscriptions, why don't you subscribe to the Milwaukee Atheists? They do some fun things too.
Maki's Atheist, Talk Heathen. I like
Yeah.
them. And like you said, the great debate community is still in full force. I know I don't do much with it any longer. I've left it for other people kind of work with it. But we're still in existence. So if you haven't joined the great debate community, link is in the video description. Come join us. We do, on the forums, we have discussions, we do posting, we let people know when the hangouts
Yep.
are, although I didn't post this one. Forgive me. I forgot.
And
but
if all this stuff becomes too serious for you, and the dumpster fires become too hot, then switch over to Pimlum's channel for a little bit of light entertainment.
yeah. Good shout out to Pit Monk. I mean, I need to go do his morning wood. I know he's offered again, and I just haven't had a chance. But Pit Monk, he is welcome to come on over here too. Have him come drop by, man.
Yeah, he's actually a smart dude. I
I
mean, I
like
know
him.
he does the country stuff pretty well, but he's actually a pretty smart dude.
I,
I
I'm
mean,
not.
for
I'm
you
not.
to,
I'm not into the crass humor that much, right?
yes,
But I know Pimp well enough to know 99% of what he does is complete bullshit act. He's a nice guy. He's smart.
he's a comedian.
Yeah,
It's
he's a
his
comedian,
bit.
right?
But the thing I find that's amazing is the stuff he's doing is improv, right?
Oh
He's
yeah.
not scripted.
No, he's
He doesn't sit there and rehearse it. It is just off the top of his head. And in order to be able to do it that fast, that consistent, you got to have a lot going on here, and I respect that. So.
Jim says he wants to hear more about fusion. We did fusion last time, actually. I mean, we have the second one we did was talking about thermal fusion. So I don't know what else we can really go in about that.
I mean, some ways,
But
I don't know, maybe with the astrophysicists, we can talk a little bit about how stars work.
yeah, no, I like to do that. I like to do something like the we can talk about the Hertzsprung-Russell diagram. We can talk about how you know what would be fascinating? Progression of theories. Like, do you remember what's called the Helmholtz mechanism? It was a
Um,
mechanism that produced that was supposedly was trying to explain how stars stay up, and it's basically a cooling rate compared to
yes.
the rate the surface area cooling rate as opposed to the energy mechanism by which the sun is staying up. But we also know now that the energy mechanism is thermal fusion, and we also know there's gamma pressure. And so that mechanism, the Helmholtz mechanism, is no longer applicable. But it made sense at the time. It was actually a viable theory at the time.
Because pre-nuclear understanding, people like Lord Kelvin was saying, well, the sun is its chemical fire, and how big is the sun? How long could the
It came.
chemical fire burn?
If
And
I
it's
it was 4 million years, I think it came out to be. If I
yeah,
remember correctly
it's
from the
somewhere in
Helmholtz.
the 4 to 5 million years.
Yeah, it wasn't very long,
But
and that's what the problem was. Wait a minute, they're like, wait a minute, we know the star. This is when the theories don't match up, right? Because they said, okay, if we take the Helmholtz mechanism, it should only be about, and again, I'm pulling this out my ass, but I think it's like 4 million years or something like that. That's not a long time because we know it's 5 billion years old, right? So this is why we
yeah,
this is why we get an astrophysicist. They probably know these numbers off the top of their head. I just know the concepts. Numbers.
I mean, this was back in the case where they're talking about essentially the sun was a big giant chemical fire that was losing heat at a certain rate.
Yeah, but they didn't know
And
what it was. They didn't know. They had no idea what the mechanism was. I don't think they believe it was fire, but they definitely didn't know
well,
what
that
the
was one
hell
of
it
the early
was.
things. Was
Kelvin did. Kelvin
Yeah.
did.
Yeah,
Yeah.
the heat. And so one of the things that they did was they said, well, now they started getting some of this notion of looking at spectra of materials, saying, well, let's look at the spectra of the sun
Yep.
and see what kind of chemicals might be going on there. And they found this element that they, with the spectral lens, had never seen before. And so they called it, the sun was, the Greek name was Helios, so they called it helium. Right?
Mm-hmm.
It was a thing that was in the sun that they never had seen on Earth. They never had been able to chemically react, and now we know that helium.
Yeah, now we know how to produce it. Yeah, now we have.
Is inert gas, but helium doesn't form compounds under normal conditions on Earth. So they never saw it in a gas chromatograph. They never saw it being burned in a fire. But they presumed, oh, there's this other substance on the sun, Helios, we'll call it helium. And so helium was actually discovered first not on Earth, but on the sun. And they thought, well, maybe this has weird properties and it's helium chemistry that we don't understand. Well, in some ways, the nuclear process, ironically, was involving helium.
Well, that's all it is. Protons converting to helium and ionized helium nuclei. But anyways, we have one last question, but we're not going to answer it today. We're going to save this for next time, so you can read up on this. But the question is, Landon, have you heard about the void in the CMB, which could be alleged to be an indicator of another universe? Crazy talk, and it's not so much another universe per se. That the thing that they're looking at in the CMB may not just be another universe. It may be literally a universe that is formed similar to ours by a quantum foam bubble, is what I've actually read as well. Because what I've seen, the way they predicted it would look if another universe was to exist from the quantum foam, not just one like next to us, but something actually created out of the same way we were, and it impacted us, it would produce that shape. And if you look at the CMB, there's a remnants of it. It looks similar like you would see for what you expect for a crater, right? If I drops something in sand, it produces a little crater, and over time it gets worn away, and if the craters on the Earth get worn away, it looks something like that. Have you seen that yet?
Yeah, and the questions are whether or not the signal is valid or not.
Could be. Yeah, who knows? But we can talk about the CMB and that kind of stuff next episode.
But that would definitely be a topic for next time.
All right, so with that, guys, thank you for watching. We are going to do a screen share out, live mic, so you can still hear us because I can't silence it, but let's play that music. And you can't hear that music, but I can hear the music, so I can jam out to this. I love this song, man. I was like, this song is like perfect for this show.
Yes, it does.
You can hear it on the outside, right? But I did. You know what? I didn't play the intro for this particular episode because I cut it short. So if you guys want to watch the actual intro to this show, go watch one of the other episodes, and we have an actual graphic intro that I did. Yes, I did it. It wasn't Kyle. I made that one. And I also made the Dumpster Fire intro for the show.
Are you? Who's playing? Are you playing?
I'm not playing this music. No, I ain't that good. This is a song that I found, free song, that just really just set the mood for this type of show. I really liked it.
We should at least give credit to.
Oh, it's I can't remember. Animetrics or something. I can't remember. They're found on YouTube. It's all free stuff. Good night, guys.